Every year, factories produce more than 10 billion battery cells, powering phones, cars, tools, and entire energy systems across the world. To top it off, over 40 million electric vehicles already rely on batteries, and billions of devices recharge daily without failure. Behind that reliability is one of the most controlled manufacturing processes in modern industry, where tiny mistakes can decide whether a battery lasts years or never leaves the factory at all. So what actually happens inside a battery factory before that power reaches your hands? Well, let's uncover it all here at the Process World. Batteries did not arrive with smartphones or electric cars. The idea of storing electricity goes back more than 2 centuries, long before factories existed to mass-produce anything. In the early 1800s, scientists were still trying to understand how electricity behaved at all. Power was something you generated once and lost immediately. That changed in 1800 when Alessandro Volta introduced the voltaic pile. It was the first device capable of producing a steady electric current. The design was simple by today's standards, yet it proved that electricity could be stored and released on demand. That single breakthrough laid the foundation for every battery that followed. As the 19th century progressed, batteries became rechargeable. Lead-acid batteries appeared and quickly found use in telegraphs, railways, and early vehicles. These systems were heavy and bulky, though they worked reliably. For decades, battery progress focused on improving durability rather than portability. The 20th century pushed batteries into everyday life. Radios, flashlights, and portable tools demanded smaller power sources. New chemistries emerged, including nickel-based batteries, which offered better performance for consumer electronics. Each step brought batteries closer to the modern world. The real turning point came late in the century with lithium-ion technology. Lithium's natural properties allowed batteries to store more energy while weighing far less than older designs. Once this chemistry proved stable and rechargeable, industries moved fast. Electronics manufacturers adopted it first. Automakers followed. Energy companies came next. That rapid adoption created a new challenge. Making lithium-ion batteries by hand or in small batches was no longer enough. The technology demanded factory-scale precision. From that point forward, battery innovation became inseparable from industrial manufacturing. So how do they do it? Well, before we get into that, please leave a like and subscribe for more amazing videos like this one. Now, moving on, long before a battery reaches an assembly line, the real work has already begun. Battery factories depend on raw materials that meet extremely strict standards. Even small impurities can shorten a battery's life or cause safety problems later on. The most important materials arrive as fine powders and liquids. Lithium compounds form the core of the chemistry. Graphite is prepared for the negative side of the battery. Metals like nickel, manganese, and cobalt are refined for the positive side. Separators arrive as thin, porous films. Electrolyte chemicals are delivered in sealed containers protected from air and moisture. Every shipment goes through inspection. Factories test purity, particle size, and consistency before approving anything for production. Materials that fail these checks never move forward. This stage exists to prevent problems long before machines start running. Storage matters just as much as testing. Many materials react badly with moisture, especially lithium-based compounds. For that reason, factories store them in climate-controlled rooms with tightly regulated humidity. Some areas stay drier than deserts. Temperature is controlled as well, since chemical stability depends on it. Preparation continues with precise weighing and batching. Each material is measured down to fractions of a gram to match exact formulas. These recipes are locked in by engineers and adjusted only after extensive testing. Consistency is the goal. Every battery cell needs to behave the same way once it leaves the factory. Once that preparation is complete, the factory stops dealing in ingredients and starts building components. This is where measured powders are transformed into the structured layers that form the core of every battery cell. The first step in this stage is mixing. Active materials arrive as fine powders and are blended with conductive carbon and binding agents. A liquid solvent is added to form a slurry. This mixture has to be consistent from start to finish. Industrial mixers run for extended cycles to ensure every particle is evenly distributed, because uneven chemistry creates weak spots that show up later as performance loss. Once ready, the slurry moves to coating machines. It is applied onto long metal foils in smooth, continuous layers. Aluminum foil carries the positive electrode material. Copper foil carries the negative side. Thickness is measured in microns and monitored constantly. Sensors adjust the process in real time to maintain uniform coverage across kilometers of material. After coating, the electrodes pass through large drying ovens. Heat removes the solvent and bonds the active material to the foil. This step fixes the structure in place. Drying is carefully controlled to prevent cracks or density variation, and the electrodes then move through heavy rollers in a process called calendaring. Pressing evens out thickness and increases density, improving energy storage and electrical consistency. The finished sheets are slit into precise strip size for the battery design. Each strip is inspected before moving forward, and these strips now become building blocks. Assembly brings those blocks together. A negative electrode, a separator, and a positive electrode are aligned in sequence. The separator allows lithium ions to move while keeping the electrodes electrically isolated. Cells are assembled either by stacking flat layers or winding long strips into compact spirals, depending on the design. Metal tabs are welded to the electrodes to carry current in and out of the cell. Automated welding ensures low resistance and long-term stability. The assembled structure is then placed into its casing, providing protection and shape. Up to this point, the battery has structure, layers, and connections. What it does not have is chemistry in motion. That changes in the next step. Electrolyte filling happens inside specialized dry rooms. These spaces operate with extremely low humidity because moisture reacts dangerously with lithium-based materials. Air inside is filtered and controlled at all times. This environment protects the cell during one of its most sensitive stages. The electrolyte itself is a carefully formulated liquid. Its job is to carry lithium ions between the electrodes during charging and discharging. Machines inject a precise amount of this liquid into each cell. Too little reduces performance, too much creates pressure problems later. Accuracy here is measured down to fractions of a milliliter. Once the electrolyte enters the cell, it slowly spreads through the internal layers. Factories allow time for proper absorption so the liquid reaches every part of the electrode surfaces. This step ensures uniform chemical behavior once the battery is activated. After filling, the cell is sealed. The method depends on the casing type. Cylindrical and prismatic cells are sealed with metal caps and laser welding. Pouch cells are heat-sealed along reinforced edges. In every case, the goal is the same: lock the chemistry inside and keep air out for the entire life of the battery. At this stage, the battery still sits at zero usable power. No charging has happened yet. The electrolyte is present, the structure is complete, the chemistry is ready. The next phase will introduce electricity for the first time and determine whether the cell becomes stable, efficient, and safe for long-term use. Through formation, the battery will be exposed to electricity. Each cell is connected to testing systems that slowly charge and discharge it under strict limits. These early cycles trigger internal chemical reactions that define how the battery will behave for the rest of its life. One critical result of this process is the creation of a protective layer on the electrodes, often called the solid electrolyte interface. This layer forms naturally during the first charges and acts as a stabilizer. It prevents unwanted reactions, improves efficiency, and protects the battery during everyday use. Without proper formation, batteries degrade quickly or fail altogether. This stage cannot be rushed. Charging too fast causes internal damage. Charging too slowly wastes production time. Factories follow carefully tuned profiles based on cell design and chemistry. Each battery is monitored for voltage behavior, temperature changes, and consistency during these cycles. After formation, cells enter an aging period. They rest under controlled conditions while engineers observe how they hold charge over time. This waiting period helps reveal defects that were not visible earlier. Cells that show abnormal behavior are removed from the production line. By the end of formation and aging, the battery is no longer an empty shell. It holds usable energy. Its internal chemistry has stabilized. Its long-term performance has already been shaped. This stage decides which batteries move forward and which never leave the factory. Once a battery has proven it can hold energy safely and consistently, the focus shifts from individual performance to how cells work together. Now, a single battery cell holds real power, though most machines require many cells working together. So factories begin by grouping cells with matching capacity, voltage, and resistance. Consistency matters since uneven cells create heat and shorten lifespan. These matched cells are connected in series and parallel to form modules using low-resistance bus bars or welded tabs. Control electronics known as the battery management system are then added to monitor voltage, current, and temperature. Larger packs also include cooling and structural protection to keep temperatures stable. After final system checks, the battery becomes a complete power unit ready for real-world use. the time a battery reaches packaging, it already works and has passed inspection. That still does not make it safe to ship, without protection. Batteries store large amounts of energy, and damage during transport creates serious risk. Packaging exists to control that risk, so cells and packs are secured to prevent movement, cushioned against shock, and enclosed in rigid protection. Terminals are insulated to avoid short circuits. Clear labels identify battery type and handling requirements, since batteries are regulated goods. Factories also ship batteries at reduced charge levels to lower transport risk. For large packs, reinforced crates and internal frames provide stability, while sensors may track shock and temperature. Packaging is the final safety barrier before batteries enter global circulation, and that's it. So after seeing how many stages decide whether a battery survives or fails, which step do you think matters the most? Share your thoughts in the comment section below. Leave a like, subscribe, and turn on the notification bell for more amazing videos like this one.